Hello everybody and welcome back to the next episode in the Project Euler archive series. Today we're taking a look at number 5. So, 2,520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest positive number that is evenly divisible by all of the numbers from 1 to 20? Okay, so this is a LCM problem. I'm just going to take up this scratch file here so I can do some explaining. So for an LCM problem, taking two numbers, for the purposes of this example, I'll use 12 and 18, and then you need to list the prime factors of each of those numbers. It's that, and then that. And then to find the lowest common multiple of these numbers, you need to, for each prime factor, find the highest frequency that prime factor appears in each number. So, for example, the number 2 appears twice in the prime factorization of 12, only appears once in the prime factorization of 18. So twice is the number we care about, and we'll keep track of that in some list. So keep track of two 2's because there are two 2's in 12, and that's the highest number of 2's. For 3's, similar situation, but there are two 3's in 18, so you keep track of that. And then the product of this list is the answer, is the lowest common multiple. So in this case, 2 times 2 is 4, times 3 times 3 is 9. So 36 is the lowest common multiple of 12 and 18. Hopefully that makes sense. That's how we're going to be solving this problem. So I will need to make a method to do the prime factoring. So prime factor of n. Oh, also, since we're only dealing with numbers up to 20, we could just make a primes list. So we don't have to make another is prime function to see if a number is prime. We could just put them in this list because it's not that many primes. Just 2, 5, 7, 2, 3, 5, 7, 11, 13, 17, and 19. Perfect. Okay, so what we'll do is we'll loop through primes and try to divide n by whatever prime we're at as many times as possible, and then move on to the next one. So for example, that's working. For example, let's say we started with the number 20. What we'll do is we'll try to divide 20 by the number 2 as many times as we can. So we'll start with 20, and we'll keep track of how many times you do that, by the way, in some kind of list. So we'll divide 20 by 2, and now we have 10, and we'll keep track of 2 in some list. And then we'll try to divide 10 by 2 again, which we can, into 5, add 2 again. Then we move on to 3. We see that we cannot divide 5 by 3, so we move on to the next prime factor, 5. We can divide 5 by 5, and we're left with 1, and then we add 5 to our list, and these are the prime factors of 20. So, as we see here, we'll have to continue doing whatever we're going to do while n is greater than 1. The index of the primes we're at, we'll call that I equals 0. And then while n is greater than 1, if n mod I, no, not mod I, if n mod primes at I equals 0, that means it's divisible by the current prime factor we're at, then we're going to do something. So rather than actually keeping it in a list, since we care about the frequency that each number appears, I'm going to store all this information in a dictionary. So we'll call it factors equals dict, right? And then, so if n mod primes at I equals 0, meaning that it is divisible by, we'll have to check if we've already seen this number before in our dictionary. So if primes at I in factors, meaning we already have an entry, then factors at primes at I plus equals 1. Add it because this dictionary is going to be the prime and then the frequency of that prime. So for example, in this example, instead of a list of being 2, 2, and 5, it would be a dictionary that would say 2 had a frequency of 2, and then the prime 5 had a frequency of 1, something like that. So if primes at I is in factors, then factors at primes at I plus equals 1, else then we have to make it equal 1 because we're creating a new entry. So factors at primes at I equals 1. Okay, that looks fine. And then what do we have to do? Do we just return factors? Oh, we got to increment I each time. Plus, and of course we got to change n, or else this loop will go on forever. So if n is divisible by primes at I, we'll keep track of it in our dictionary, and then n divide equal primes at I. Okay, so let's just see if this works. I'm going to print prime factor of, let's do 18. Just as an example, see if it works. So Python 3 5.py. Got an error. So it says list index out of range on line 10. N mod primes at I equals 0. So why would that be out of range? Oh yeah, because I'm just adding I each one. So I don't need to increment I by 1 each time. I only increment I if this doesn't work. So yeah, then we need an else. So if n mod primes at I, if it's divisible by primes at I, then we do all of this stuff. If it's not divisible by primes at I, that means we should move on to the next prime, because we've already exhausted the amount of times we could divide by the prime we were at currently. So in this else block, we'll say I plus equals 1. Okay, so for 18, yeah, we have the prime factors of 18. There's 1, 2, and 2 3s, which makes sense because 2 times 3 times 3 is 18. Okay, so this method is working just fine. Now we need to do the rest of the problem. Okay, so like I said before, in the example with 12 and 18, 18 was 2, 3, 3. So you need to go through each entry and keep track of the highest occurring one. So I suggest that we have some kind of, let's call it all factors, some dictionary all factors. Okay, and it's going to be dictionary of the frequency of each prime we see. So it's going to have like 2, 3, 5, and so on. So for example here, we would go through 12 and see that there's 2 2s, and there's only 1 2 in 18, so under 2, there's 2 2s is the maximum. And for 3s, there's also 2 3s, which is the maximum. And then once we've populated all factors, we could just, do some math and find the correct result. So let's do that. For I in range 2 to 21, because we want to include 20, I'm going to create all factors up here. Okay, so for in this range, first we need to start by finding the prime factors. So say factors equals prime factor of I. Okay, now we have our prime factors, and then for let's say f for factor in factors. So for example, if we were at 12, we'd be going through the dictionary. So like, it's not like this actually, it's more like, I have these all as lists, but it'll make more sense if I show them as dictionaries. So 12 would be like 2, 2, and then 3, 1. So for f in factors, if all factors, if f is in all factors, meaning we've already seen this before, then all factors at f equals the max between what we already have already, all factors at f, and factors at f. So just the maximum frequency, updating that max frequency if we need to. Else, if f is not in all factors, then all factors at f equals factors at f. Okay. And this should populate all factors properly. So let's check all factors. Print all factors. Okay, so we got there's 4 2s, 2 3s, 1 5, all this stuff. Looks fine to me so far. Let's have to test it. So now that we have all factors, we need to go through all factors and find the product. So I'm going to say prod equals 1. And then for f in all factors, prod times equals all factors. No, prod times equals the f to the power of all factors at f. Yeah, so what this will do is, like, for example, for f in all factors, let's say all factors is this here, prod would times equal 2 to the power of 2, or 3 to the power of 2. That's all that's saying. And then print prod. Okay, so this huge number, let's see if that is correct. All right, we're 5 for 5. We got another one. That was a bit harder. That took a little longer. This video went over 10 minutes, but I'll see you in the next video.